Hi everybody. So in today's AP review video, which is our fourth AP review video, I'm going to start to go over a couple different topics that are often related to each other in a variety of FRQs. So the first thing that we're going to do is review two strategies for finding a derivative of functions that are defined a bit differently than just a straightforward function. And the first thing we're going to review here is what's called implicit differentiation. Now, implicit differentiation is a process for finding a derivative that we use when a function is defined implicitly. So we're going to start by reviewing what that means. A function is defined implicitly when the y in the function is not isolated. So in other words, you don't have the y by itself. When we take the derivative of an implicitly defined function, we need to write dy over dx or a similar derivative notation each time we take the derivative of the y. Now, it's important to note here that we can use a variety of variables for this type of scenario. So we could also use functions that are defined with variables like you'll see at the bottom of this page where we're using g's and t's instead of x's and y's. And so we will talk about that in a few minutes. How do you kind of handle using a variety of variables in this scenario? The first thing I'd like to review is when we find the first derivative. So a lot of times it's going to say, if this is your function, find dy over dx in terms of x and y. Now this phrase right here, in terms of x and y, is really important because what that means is that we want our final answer to have both x's and y's in it, and we don't want anything else like dy's over dx's as part of our final answer equation. So we are going to need to do a little bit of algebraic manipulation here to get the equation to look the way the problem is asking us to make our equation look. All right, let's go ahead and review how to take this derivative. So the first thing I would do is one term at a time, take the derivative of each piece of this original equation. So the derivative of 2y cubed would be 6y squared. And because I'm finding the derivative of y here, I would put times dy over dx to represent the derivative of y. Now the next term is a little bit more complicated, and the reason that this term is more complicated is that we need to use product rule to find the derivative of that term of the original equation. And the reason is because there's both an x and a y being multiplied together, which tells me I need to use product rule. So I'm going to put a plus, and then I'm going to put a big bracket so that I kind of have a place to put all the pieces of my product rule. Now to do product rule, I'm going to copy the first, which is 6x squared, take the derivative of the second, and the derivative of y is just going to be times dy over dx. Plus, and now I'm going to copy the second, which in this case is y, and then take the derivative of the first, which in this case would just be 12x. So that entire group of terms is all just the derivative of that second term of the original, the product. Then I can continue. So the derivative of negative 12x squared would be negative 24x. And the derivative of 6y would be plus 6. And then again, when you take the derivative of y, you have to write dy over dx. Now, the reason that there's nothing except for the 6 here is that the derivative of 6y is just 6. But then I have the dy over dx because that's the dependent variable in the equation. So I have to write dy over dx for that. Equals, and the derivative of the number 1 is 0. Now that's the part that I always used to make a mistake with. I would get so focused on just kind of doing these complicated derivatives that I would forget that the derivative of a number is just 0, and it would screw up my final answer. So that is one thing that I would watch out for if I were you. Now we need to do a little bit of algebra. Our goal here is to have an answer where it says dy over dx is equal to some kind of equation that has x's and y's in it. And right now the dy over dx is not by itself. It's not isolated, so I need to do some algebra to make that happen. So the first thing I'm going to do here is I'm going to take all the terms that don't have a dy over dx. So this y times 12x and this negative 24x. And I'm going to move both of those to the other side of the equation so that I can get all the stuff that does have a dy over dx in it together on one side and everything else on the other side. Now what that means is that the 6y squared times dy over dx is staying on the left side, plus the 6x squared times dy over dx is staying on the left side, plus the 6 times dy over dx is staying on the left side. Now on the right side, if I add the 24x, then I'm going to have positive 24x. And if I subtract the y times 12x, I'm going to write that as 12xy. The next thing I'm going to do is I'm going to factor a dy over dx out of all of the terms on this side of the equation. So in other words, I'm going to put the dy over dx on the outside of the parentheses, and I'm going to put whatever's left over from each term on the inside. So that would be the 6y squared plus the 6x squared plus the 6 equals, and on the other side of the equation, I still just have the 24x minus 12xy. All right, the next thing I want to do here is divide by this 6y squared plus 6x squared plus 6 in order to get the dy over dx by itself. So what that means is that my new equation, and I'll write this up here so that I have some extra space. My new equation is going to say dy over dx equals, and I'm going to have 24x minus 12xy over 6y squared plus 6x squared plus 6. And then we have one last step that we want to do. So one thing that I'm noticing is that all of the terms in this problem, the 24, the 12, and the 6, and the 6, and the 6, are all divisible by 6. All these coefficients are divisible by 6. So to simplify this, I'm going to divide them all by 6, which means I get dy over dx equals, and if I divide by 6, my new coefficients are going to be 4x minus 2xy, and then y squared plus x squared plus 1. And that would be my final answer. So now that we've reviewed how to find the first derivative, the next thing I'd like to review is how to find the second derivative, because I'm going to be honest with you, this comes up quite often, almost more often than just finding the first derivative using implicit differentiation. You're often asked to find the second derivative. Now, one scenario where you might be asked to find the second derivative is if you are trying to determine whether an estimate is over or under. So as we reviewed in our previous video, we can determine whether our estimate, especially using a tangent line, is an over or an underestimate using the concavity of the function. So since the second derivative is telling us about concavity, this might be a scenario where you need to find the second derivative in order to answer that question. Sometimes the question will remind you to find the second derivative to find that answer, and sometimes you have to just know that you need the second derivative. So it's important to realize that this does come up quite often, especially with determining whether estimates are over or under estimates. So in order to do that, we're going to find the derivative of the equation that we already have in terms of x and y. Now this is really important here, this in terms of x and y part. And the reason that this is really important is because, again, we want our final answer to have d squared y over dx squared equal to something that has only x's and y's in it. And that might require a little bit of algebra on our part, so it's important to remember that we need to do that. So let's go ahead and start by just taking the derivative. Now in this problem, I'm going to need to use product rule again, because again, this is the product of y squared and the quantity 6 minus 2x. So product rule is going to be necessary for finding this derivative. So the second derivative, d squared y over dx squared will equal, I'm going to copy the first, which is y squared, take the derivative of the second, which would just be negative 2. Plus I'm going to copy the second, which would be 6 minus 2x, and then take the derivative of the first, which would be 2y, and then times dy over dx. Okay, now that I've done product rule, this is where this part of the directions becomes really important. The problems that says find the derivative in terms of x and y. So we are not allowed to have dy over dx in part of our answer. Instead, what we're going to do is we're going to replace the dy over dx with what we know that dy over dx is equal to. So we have to plug that in because dy over dx is not allowed. We want our answer in terms of x and y. So what I'm going to do is take this equation, y squared parentheses 6 minus 2x, and replace dy over dx with that equation. So here's what that's going to look like. I'm going to have negative 2y squared. I'm just simplifying this term, plus parentheses 6 minus 2x times 2y times, and now I'm replacing the equation with y squared parentheses 6 minus 2x. Now we're going to simplify. So if I simplify this, I'm going to have negative 2y squared plus, now the 2y times y squared is going to make 2y cubed. And then 6 minus 2x times another 6 minus 2x would make 6 minus 2x squared. Now that is how I would leave my final answer. Now there is one more example problem here, and the reason I included this in our notes is because this is a very common way that students kind of get tripped up on the AP test. This is a common mistake that I often see when I'm looking at student work as we prepare for the AP test. So one of the things that's really important here is to realize that we don't always use the variables x and y. When we see x's and y's, our brains are trained to recognize that the y is special, and so we need to do something special. We need to write dy over dx. The issue that I always find is that when a problem uses g's and t's, or very often other variables and t because it's something changing with respect to time, the students that I've graded who have trouble with this have trouble remembering that the g in this scenario is acting like a y. So because of that, every time we take the derivative of g, we're going to need to write dg over dt. So here's how I would do this problem. One of the kind of tricks that I have for making this a little bit easier is that we can avoid product rule for this type of problem because we can actually distribute the 3. So when we distribute, we get 6d minus 3g. Now I do want to note here, if there was a power, like a 4th power on the outside of the parentheses, we cannot distribute. Order of operations prevents us from distributing because the power operation would have to happen before the multiplication. So in that kind of a scenario, we would not be able to distribute. But in this scenario where there's no power here, we can distribute. And that can make our life a little bit easier because we don't need to worry about product rule or how we handle any kind of coefficient. So I'm just going to distribute to make the problem easier to take the derivative. Now, because the g is acting like y, when I take the derivative of g, I'm going to need to write dg over dt. So the second derivative here, d squared g over dt squared, would be the derivative of 60, which is just 0, and then the derivative of negative 3g, which is negative 3, and then dg over dt, because the derivative of g would be dg over dt. Now, just like in our previous problem, we're going to need to replace the dg over dt with what we know is the equation for dg over dt. So I'm just going to go ahead and plug that in, which means I get that my second derivative, d squared g over dt squared, is equal to negative 3 times 3 parentheses 20 minus g. Now, some students often ask me, are you allowed to simplify? Should you simplify? How do you simplify? And my answer would be this. This is a perfectly acceptable answer. You can leave the answer to your question just like this. You could also distribute the negative 3, and you could get negative 9 parentheses 20 minus g. You could distribute the negative 9, and you could have negative 180 plus 9g. You could distribute this 3 and leave this 3 on the outside, and you could have negative 3 times 60 minus 3g. Any of those are acceptable answers and acceptable ways to simplify because they are all mathematically equivalent expressions. My suggestion would be that if you don't need to simplify, don't bother simplifying because you run the risk of doing it incorrectly. So I would just leave my answer like this and be done with it. All right, let's take a look at the next page. On the next page, we're going to be reviewing a different topic. So this second topic of these notes is finding the derivative of an inverse function. Now, this is something we did way back a long time ago, so I'm sure that it's something that we need to review. And I want to review that we find the derivative of an inverse function using chain rule. So just like with implicit differentiation, there's this process that we follow. So in order to find the derivative, there's this process that we follow when it's an inverse function, and that is to use the chain rule to find the derivative. After you find your derivative, then you still need to usually substitute your x value and actually solve the problem. So we're going to go through this kind of step by step and just make sure that we have an idea and a review of how to do this process. Now, these problems are often tied up with a table problem. So we're going to use this table for both scenario here and this scenario here. So let's go ahead and take a look at this problem. It says if p of x is equal to f inverse of x. So as soon as I see this, that should trigger that this is an inverse function, and there's like a step-by-step process that I need to follow to find the derivative. Find p prime of 10. Well, in order to find p prime of 10, I need to have p prime. And right now, to take the derivative of p, I would need to take the derivative of the inverse of f. Now, one thing that I know about inverses is that they're not as easy to work with as problems that don't have inverses. So my first step for these kinds of problems is always get rid of the inverse function. Now, in order to do that, we need to undo an inverse, which means use the original. So we're going to do what I call f both sides, which is a weird way of saying it, but we're basically applying the f of x function to both sides, which means we have f of p of x equals, and f inverse cancel, so we just have x. Now we can actually take the derivative using the chain rule. So we would start with the outside. F prime of, leave the inside alone, p of x times the derivative of the inside, p prime, is equal to the derivative of x, which is just 1. Then, in order to isolate p prime, because that's what we wanted, we needed an equation for p prime so that we could plug in our 10. We would just divide by the f prime of p of x. So p prime of x would be 1 over f prime of p of x. Once we do that step, it's time to move on to the second step, which is basically take the 10 and plug it in. Now here's where it gets a little bit tricky. So if we plug in the number 10 for all of the x's in this equation, we're going to have p prime of 10 equals 1 over f prime of p of 10. Now, we need to know p of 10. The first step to evaluating this would be to figure out what is p of 10. The issue is that we don't have any information about p in our table. We only have information about f and about g. So here's where we need to go back to the fact that these are inverse functions. If we want to plug in the number 10 to p, then because of the relationship between inverse functions, if p is the input 10, then 10 is the output of f. Now that's going to allow me to use the table because now I'm talking about the f of x function, which I have in my table. If this is the output, then I'm going to look for that number in the output column for f. And I'm going to find the number 10 right here. I can use that to go backwards and find the corresponding x. Now, again, because of the relationship of inverse functions, that means that the output here would be 3. So if the input of f is 3, then the output of p is 3, which means this value is really just 3. So I would have 1 over f prime of, and p of 10 we have now figured out is 3. Again, I can go back to my table to find this information. So f prime of 3 just means look at the f prime of x column. When x is 3, f prime is -4. So p prime of 10 would be 1 over -4. And that would be my final answer. All right, now in my next example problem here, going back to this idea of finding the derivative of the inverse function, is that sometimes we need to find that derivative as part of a longer process. So one of the things we can ask you, and that we are often asked on the AP test, is to write the equation of a tangent line. In order to write the equation of a tangent line, we've already reviewed that we need two pieces of information. We need a point and we need a slope. After we have our point and our slope, we can actually write the equation of the tangent line. Now, in this scenario, it says if f inverse is the inverse function of f, write an equation for the line tangent to the graph of y equals f inverse of x at x equals 9. Now, the reason I know I'm going to apply this process for inverse functions is that this is telling me that I'm looking at the inverse of f. So one thing that I find a little bit challenging about the way that this problem is phrased is the notation here. Y is equal to f inverse of x. I prefer it when we actually have a separate function, p of x or g of x or h of x. It's just easier for me to work with. So I'm going to replace the y with g of x. For the rest of this problem, I'm just going to use g of x instead of y. It's just an easier notation for me to work with. Now for my point, it's telling me that the input of the inverse function is 9. Now if I go to my table, what that means is that if the inverse function has an input of 9, then the regular function has an output of 9. So I'm going to find the number 9 in my table in the output column for f. And I'm going to map it back to whatever the corresponding x value is, which in this case is going to be the number 2. Now let's also not forget that f inverse is what I'm using g for in this problem. So now that I've got that point figured out, I'm going to work on the slope. Now to get the slope, I'm going to follow the same kind of process I followed here. So I'm going to f both sides. So I'm going to have f of g of x equals x. I'm going to take the derivative, so f prime of g of x, and then apply the chain rule times g prime of x is equal to 1, which means g prime of x is equal to 1 over f prime of g of x. Next, I'm going to plug in my value. So the value that I'm trying to plug in here is going to be the number 9. So I'm going to replace all these x's with 9's, which means I'm going to have g prime of 9 is equal to 1 over f prime of g of 9. Now we already know, because we mapped it out earlier, that g of 9 is just 2. We can get that from this information that we mapped out earlier. So what I really have here is I have g prime of 9 is equal to 1 over f prime of 2, and I can get that information from my table. So that would be 1 over f prime of 2 is just 2. So there's my slope. Finally, I'm going to write the equation of my tangent line. So my tangent line would just be y minus 2 equals my m, which is 1/2, times x minus 9. I think there are really two key things that you need to do in order to be successful in these types of questions. And the first key thing is knowing how to use this table of values. So it's really important to list out the information that you know. It tells you where to look in the table. If I want the input of P to be 10, then the output of F is 10. If I want the input of the inverse to be 9, then the output of the original is 9, kind of making those connections. The second thing that's really important is if they ever give you a notation like this, y equals f inverse, replace the y with a more comfortable notation like g of x to make your life a little bit easier. All right, next we are going to look at problems with differential equations. So a common free response question on the AP test is a problem where they give you a differential equation. One of the things that they can ask us to do in a problem with a differential equation is to graph a slope field. In order to do this, you're going to be given a differential equation. So the problem will already have an equation like this in the directions. Then you're going to substitute, which means plug in ordered pairs, x's and y's, into this equation. And then that will tell you the slope of the line segment that you're going to graph. Now, what's really important is to remember that positive line segments look like this, positive slopes. Negative slopes look like this. Zero slopes are flat, and undefined slopes are vertical. So it's important to remember that your slope needs to match the slope that you calculate. Now, they're not super picky about how steep the lines are, so you don't have to have like certain steepness, but you do need to have lines that are pointed the right directions. Now, another thing that you can often be asked to do on the AP test is to graph a particular solution on a given slope field. So in this case, you will already be given the slope field. Either you would have had to make one yourself or it was already given in the problem before you even did anything. You need to make sure you find the specified starting point. This is really important. It's going to give you a point to start at and say, draw the solution that goes through this point. If you start in the wrong spot, your solution is going to be wrong. So pay attention to the scale of the graph. Make a curve that follows the flow. Don't overthink it, just go with the flow. And then finally, make sure that your final graph is a function. So you want to make sure that it passes the vertical line test. If you feel like your graph should be a circle, it should not be a circle because a circle would not pass the vertical line test. So if your graph feels like it should be a circle, that is wrong. Instead, you should have a graph that's either just the top half of the circle or just the bottom half of the circle. But your graph is never going to be a full circle because it does not pass the vertical line test. A third piece of the puzzle here, and this has been on every AP test that I've ever seen, is to find a particular solution to a differential equation using separation of variables. Now, here's the thing. Sometimes these are hard to identify because the problems do not always have x's and y's in them. Just like when we were looking at applying implicit differentiation to problems that have other variables, when we start throwing other variables into these scenarios, it does become harder to identify that you need to do this. So step number 1 here is going to be to separate the variables. It is an automatic 0 points if you miss this step. And here's what I mean by separate. You want all of the stuff that has a y with the dy on the left side, and you want all of the stuff that has an x with the dx on the right side. And another example could be you want all of the stuff that has a g with the dg on the left side, and you want all of the stuff that has a t with a dt on the right side. So it doesn't matter what the variables are, but you've got to kind of get those pieces separated. Next, you're going to integrate on both sides. And it's important to know that you need to integrate because in order to do the opposite or the inverse operation of a derivative, you need to do an antiderivative. Don't forget to put a plus c. We usually do this on the right side only. Then you're going to solve for c using the initial value. The initial value is often given in the directions to the problem. So please make sure you're reading carefully. That's kind of a common theme throughout our review. You got to read carefully. Finally, you're going to plug in your c to your equation and isolate your y, or whatever the dependent variable would be. In this case, that would be g. Really, the biggest issue here is to watch out for other variables. If you take the AP test and you do not separate the variables and do antiderivatives and find your C, if you don't do this process at least once, you missed it. It's been on every AP test I've ever seen. So watch for it, look for it, and have it in mind while you're working. All right, the last thing I'd like to review today is some of the ideas related to particle motion. Now, on this year's AP test, where they're not assessing Chapter 8, there's a lot of limitations to kind of what they can ask about particle motion, but there are still some things that will be covered. So I'd like to review those things now. One thing I'd like to review is that in particle motion, we usually use v of t for your velocity function, and we usually use a of t for our acceleration function. And I'm going to use that notation throughout this set of notes. Another note is that oftentimes we use s of t for position function, although that is a little bit more flexible. Sometimes problems will use x of t or y of t if it's a particle that's moving along a straight horizontal or a straight vertical line. So I will be using kind of those functions throughout these notes. If a problem ever asks me to find position, there are two ways to do this. Option number one is to use your s of t function and plug in your t value, your a. Option number two is to use your velocity function. So to find your position, you would do your initial position, which is usually given in the instructions somewhere, plus the integral from your initial time to your a value, whatever value you're trying to find the position at, and then use your velocity function inside of the integral. Now, here's why I'm showing you this. It depends on what you have. You might find your position just using a position function, or you might have to find your position by doing an integral, the initial plus the integral of velocity, because we don't know what information we're going to be given. If we don't have a position function, we can't find it that way. So I do want you to know that you do have options here. Now, for finding displacement, I want to review with you that displacement is just the change in position. So instead of being asked to find displacement at a certain time, it will be over an interval of time. So it'll be from A to B. There are, again, two ways to do this. Option number one is to use your position function and you find the position at B, so your ending position, minus the position at A, your initial position. The second option, though, uses your velocity function. So the second option for finding displacement would be to integrate from A to B your velocity function. because that's going to give you the change in your position, which is your displacement. And again, the A and the B are the numbers from the interval that you're using. Now, average velocity is the slope of your position function. And average velocity just means average slope. So to figure this out, you would take your position function and do regular old slope. So plug in the final time minus plug in the initial time over this particular interval, all over b minus a. As a reminder, this is basically y2 minus y1 over x2 minus x1. Now, instantaneous velocity is a totally different idea because instantaneous velocity just means the derivative of position. So you could take the derivative of your position function and then plug in your a value. Or if you already have your velocity function, you could just take your velocity function and plug in your a value. You don't need to then do the derivative. You've already got the right equation. Now, moving to the right, moving to the left, or stopped are all questions that are related to velocity. So these are all going to be related to the sign of velocity. Now, there are two different ways these questions can be asked. They could ask you in general, find me all the times when you're moving to the right, moving to the left, or stopped. If they ask you in general, so find all times when these things are happening. The first step would be to take your velocity function and make it equal to 0. Now that might mean that if you have position, you have to actually take the derivative, but you want to set that equation equal to 0. Then you're going to make a chart. And in your chart, you would take all of your t values and you would divide up the chart into sections, and you would look at the sign of velocity. So each section would have either a positive or a negative sign. All of the positive signs are going to be places where you're moving to the right, and all of the negatives are going to be moving to the left. And you calculate these values by plugging them into V. So pick a number in between these two numbers and plug it in. Now, if I want to know, the second option is if I want to know just am I moving to the right, am I moving to the left, or stopped at a particular time, you're just going to plug your number into your velocity function. If your velocity value is greater than 0, then you're moving to the right. If your velocity value is less than 0, then you're moving to the left. And if your velocity value is equal to 0, then your particle is stopped. Now, as far as times when a particle changes direction, this is very closely related to what we just talked about. Stopped is very closely related to changing direction. However, just because a particle stops does not mean it's guaranteed to change direction. I like to think about this as driving a car. Just because I stop at a stop sign doesn't mean I turn. I could keep going the same way. So what we want to do is see if v of t changes signs. Now you could do this by making a graph of your v of t function. So if you've got a calculator, you could actually graph your velocity function and see where it changes from positive to negative or negative to positive. In other words, above to below or below to above. The other option is you could follow kind of the same steps as here. You would take your velocity function and make it equal to 0 and get a bunch of t values. Then you would set up a signs chart. And in this chart, all of those values that you found will become like the dividing lines in the chart. And then you would look at the sign of V. You're looking for where these change signs. Now let's talk about acceleration. So this is kind of all stuff that's related to position and velocity. Acceleration is the second derivative of position. So if I ever ask you to find the average acceleration, the average acceleration is a lot like the average velocity, only instead of being the slope of the position function, it is the slope of the velocity function. And since it's the average slope, we would just take our velocity function and find regular old slope. So v of b minus v of a all over b minus a. Now, instantaneous acceleration, just like instantaneous velocity, is the derivative of velocity. So just like instantaneous velocity is the derivative of position, instantaneous acceleration is the derivative of velocity. So you would need to take the derivative of velocity and plug in your value. Now, another scenario would be if you actually have the acceleration function already, you could just take your acceleration function and you could plug in a, whatever the value is. Now, speed is a little bit different. So speed is looking at how fast an object is going, but not direction. If a problem ever asks you to write a function for speed, we would say that the speed of a particle can be calculated by doing the absolute value of your velocity function. So you would find your velocity function and just put it inside of an absolute value. If the problem ever asks you for the speed at a certain time, then you would take your a value, plug it into your velocity function, and take the absolute value of your final answer. So after you plug in your number to velocity, then force your answer to be positive. Now, if we ever ask you for whether your speed is increasing or your speed is decreasing, this is going to be a combination of velocity and acceleration. So that's one thing that's really important is speed increasing or speed decreasing. A lot of students think that that's just acceleration. It's not. It's a combination of velocity and acceleration. If they just ask you in general, find all of the times where the particle is speeding up or where the particle is slowing down, then what you're going to do is find your v of t function and set it equal to 0, and find your a of t function and set it equal to 0. Take all of those t values and make one big chart. So step 2 is going to take all of those t values and make one big chart, only this chart is going to have 2 rows. One row for velocity and one row for acceleration. Then you're going to look at the 2 rows together. If they have the same sign, so they're both positive, you're going to be speeding up. Or if they're both negative, you're going to be speeding up. Or if one is positive and one is negative, you're going to be slowing down. So in general, if v of t have the same signs, v of t and a of t have the same signs, then you are speeding up. And if velocity and acceleration have opposite signs, then you're slowing down. Now, if a problem says, hey, tell me whether you're speeding up or slowing down specifically at this t value, then just plug it in to v and A and see if you have the same signs or opposite signs. Now, one thing that I think is really important is to remember that for a lot of this, your calculator can help you out. Don't forget that your calculator can find derivatives. You can find your derivative using math option 8. So you might, for example, if you want to find your velocity at a certain time, you might type in to find the derivative of position at that time. Your calculator can also find integrals, which is just math option 9. So if you wanted to find displacement and you needed to integrate velocity, you might just let your calculator do that work for you. And your calculator can make a graph, and this might be the most important thing that your calculator can do. Because once you have a graph, you can find the x-intercepts, the maximums, the minimums, the y values, all of it. It can be really, really helpful to make a graph of f prime or make a graph of velocity, because that would allow us to answer a lot of these questions. All right, thank you guys so much for watching. I hope that you find this video helpful, and I'll see you soon.